Okay, what we're looking at is a B&K model 1580, 100 megahertz dual trace oscilloscope with delayed sweep capability. This particular model reads 100 megahertz in 23 different range steps, going from as slow as 0.5 seconds per division to as fast as 20 nanoseconds per division. We can independently read our source from channel 1, channel 2. We can read both together, and we can do an additive or subtractive read of the two signals together. It reads AC and DC, and also has an external trigger input to allow you to sync to an external source. We're going to go ahead and give this thing a quick check, but first, I'm just going to take a look at it. It's a very nice looking unit. It's in good shape, handsome. Has a nice stand. And a very nice front panel. We have plenty of intensity, as you can see. Take it from a no intensity to normal to full. Plenty of intensity. CRT is working quite well. We can position our A trace anywhere we want within the screen. I'm going to go ahead and put her on ground, make sure we have it centered. Okay. And we're going to go ahead and step this thing through some DC. We are on 5 millivolts per division on the vertical. And I am going to step 2 divisions at a time with an input voltage from this DC voltage standard. It's an analogic standard. And I'm putting in 10 millivolts. And as you can see, we jumped 2 divisions. And there is 20 millivolts, and we are now 4 divisions up. And we have 20 millivolts on the signal, so yeah, good. Let's bring that back down. And let's turn this off. I think we're getting a glare here. And we'll turn up the scale so you can see the grid. Okay, and we'll turn down the illumination just a little bit. There we go. Alright, now let's try this once again. 10 millivolts, 20 millivolts. Alright, let's go to the 10 millivolt per division. This time we're going to go up 1 division at a time. 1, 2, 3, 4. Okay. Let's go 20 millivolts. We're going to go a half step at a time. 1 division, half step, 2 divisions, half step, 3 divisions, half step, 4 divisions. Okay. 50 millivolts per division. We're going to go 2 divisions at a time. 1 step, that's 2 divisions. 2 steps. So we are going right now at 50 millivolts per division times 4 divisions, 200 millivolts, and that's exactly what we have put in, 200 millivolts. So let's get that down. Okay. Take that back. 1 step, 2, 3, 4. So 0.1's volt per division right now. 0.1 volt per division. 1, 2, 3, 4 divisions is 0.4 volts. 400 millivolts, and that's exactly what we did. Alright, and let's go to 0.2 volts per division. I'm now on 0.2 volts per division. And we go half step, whole step, half step, whole step, half, whole, half, whole. Okay, 0.5 volt per division. Okay, and we're going to go 0.5 volt per division. We're going to go 2 divisions at a time. 1, 2 steps. Okay, 1 volt per division. We're going to go 1 step at a time. We're on 1 volt per division. 1, 2, 3, 4. And we'll go 2 volts per division. We're going to go a half step at a time. Half, whole, half, whole, half, whole, half, whole. Okay. And then the final is 5 volts per division. And the best I'm going to be able to do is 1/5 of a division at a step. So here's 1, 2, 3, 4, 5. There's 1 full step. 6, 7, 8, 9, 10. 2 steps. So channel A checked out very well for DC. We're going to move to channel 2 now. Channel B, or 2 on this machine. And change our input. Check our 0. Alright, come on. Probably the hardest part of the whole thing. Okay. And we want to trigger on 2. There we go. Just move my trigger switch to 2. Okay, we are on the lowest setting of 5 millivolts per division. Sorry, 5. It's okay. 5 millivolts per division. I'm going 2 steps at a time. It's 10 millivolts per step, and then 20 millivolts. Okay, and then we go to 10, and now we go go to 10, and now we get 1 step at a time. 1, 2, 3, 4. That's 10 millivolts per division times 4 is 40 millivolts, and we were going 10 millivolts at a step. Okay, here's 20 millivolts. The 0 held. We're now on 20. And we're going to go half step at a time. Half, whole, half, whole, half, whole, half, whole. That was 80 millivolts full scale. 4 times 20 millivolts is 80 millivolts. And that's what we had in. Okay, 50 millivolts per division. And we're zeroed. It's good. And we should go 2 divisions at a time. 1, 2. 1, 2. Okay. We are at 0.1 millivolts per division. And we're going to go one step at a time. 1, 2, 3, 4. Point 2 volts per division, half step at a time. Half, whole, half, whole, whole, half, whole. Okay. 0.5 volts per division, we're going to go 2 divisions at a time. That's the first step, and there's the last step. So 0.5 volts times 4 is 2 volts, and that's what we put in. So we had 1 volt at a time for 2 division steps. We're now going to move to 1 volt per division, and we're going to go up 1 volt at a time. So we'll see 1 step at a time. 1, 2, 3, 4. Sorry. 1, 2, 3, 4. Okay. 2 volts per division, we're going to go up a half a step at a time. Half, whole, half, whole, half, whole, half, whole. 5 volts per division. And we're going to go up. We're going to go up 1/5 of a division at a time. 1, 2, 3, 4, 5. It's a whole step. 1, 2, 4, 5. 2 whole steps. That would be 10 volts in 2 steps. 5 volts per division, 10 volts. So we did it. We went through channel B, and it too is remarkably accurate for DC. So now we're going to take a look at the time base and see how we do with our horizontal sweep. I'm going to hook it up to our signal generator, which will be this Hewlett-Packard 3320B, which produces a synthesized frequency. Its variables preset by these dials. It's immensely accurate. Far more accurate than we'd be able to measure on the scope. So we're going to use that to test it. So let me hook it up and we'll be right back. Okay, we are hooked up to the HP 3320. We're feeding the timing signal into both channels simultaneously, actually looking at the display of both channels simultaneously. There we go. And we right now are at 0.5 seconds per division, half a second per division, and I am feeding in a 2 Hertz signal, and we are seeing a full cycle per every division. Now, admittedly, that might not be easy for you to see, but if I expand this scale, go from 0.5 volts or 0.5 seconds per division to 50 milliseconds per division, a factor of 10, then what I see is that let me adjust it so it's easy to see here. There, we got the timing starting right at the edge of the grid. It comes half a cycle, comes right through the middle of the grid, and it exits exactly on the right side of the grid. So we're getting 1 full cycle in 50 milliseconds for 10 divisions. So we must have had 1 full cycle at 0.5 seconds per cycle per division, and that's what we had displayed. So we're reading this accurately. Let's go ahead and move to 0.2 seconds per division, and With 0.2 seconds per division, I would like to be running 5 Hertz. Okay. And I should be seeing a full cycle for every one of these divisions. Again, not an easy thing to see, but it could be happening. So let's go ahead and go by a factor of 10. And once again, begin on the left, crossover in the middle, exit on the right. One cycle in 20 milliseconds. 20 milliseconds here. So, going at 0.2 seconds, I've got one cycle showing for every one of these divisions. Was accurate. Alright, now I'm at 0.1 second per division. I want to go to 10 cycles. Alright, we are running at 10 cycles per second. We are at 0.1 second per division. So at 10 cycles a second, we're going to get one cycle in every division. Again, it looks like we could be getting that, but it's not easy to see. So if I raise my range up by a factor of 10 and observe, I see that I enter on the left, cross over in the middle, and exit on the right in one cycle for 10 divisions. So when I was going at 1/10 of the speed, I'm going to do one full cycle in every division. That's accurate. Alright, now we're at 50 milliseconds per division, and that would be 20 Hertz. And we'll test that by going factor of 10 again. Enter on the left, cross over in the middle, exit on the right, one cycle in 10 divisions. So we have one full cycle in one division at 50 milliseconds per division. Okay, let's go to 20 milliseconds per division. And we raise up to 50 Hertz. I have one full cycle per division. It's getting a little easier to see because our phosphor is getting repainted fast enough for us to see a more persistent trace. So if I adjust myself here, I can see that I am entering right on the left side and I'm exiting right on the right side. Perfect. One cycle. And we can test that again by going a factor of 10 on the range, and we see that we enter on the left, cross over in the middle, exit on the right. 10 divisions. Alright, we're at 10 milliseconds per division, and I want to go to 100 Hertz. And kick my intensity up a little bit. Okay. And we should be able to see that enter on the left, cross over in the middle, and exit on the right on every division. Okay. And we can test that again. Factor of 10 on the range. Enter on the left, cross over in the middle, exit on the right. 10 divisions. 5 milliseconds per division. We want to go to 200 Hertz. Okay. And we should see now that we are painting a cycle in every division. And if we look, we see that we enter on the left, cross over in the middle, and exit on the right in every division. Easier to see if I set my range up by a factor of 10. Enter on the left, cross over in the middle, exit on the right, 10 divisions, 200 Hertz. Two milliseconds per division. Go to 50 Hertz. I'm sorry, 500 Hertz. We're at 500 Hertz now. I'm going to, by the way, did you notice there's two traces there? I have the two traces superimposed on one another. And they trace perfectly. I think that's impressive in itself. Okay, so we enter on the left, cross over in the middle, and exit on the right, every division. Factor of 10. Enter on the left, cross over in the middle, exit on the right. 10 divisions. Now we go to 1 millisecond per division. We go to 1000 Hertz. Okay, 1 kilohertz. Enter, cross over in the middle, exit on the left, every cycle. Factor of 10. Enter on the left, cross over in the middle, exit on the right. And this is 0.1 millisecond per division. Go back to the 1. So we must be hitting it in every division, like I said. Perfect. Alright, we are now at 0.5 milliseconds per division. I want to go to 2 kilohertz. Alright, and enter on the left, cross over in the middle, exit on the right. We are 1 division for every cycle. Easier to see times 10. Enter on the left, cross over in the middle, exit on the right. That's 200 Hertz. And we're displaying 10 divisions at 50 microseconds per division right now. Going back to 0.5 and then up to 0.2. At 0.2 I want to be 5 kilohertz. Okay, 5 kilohertz. Enter on the left, cross over in the middle, exit on the right, 1 in every division, no problem. Times 10. Enter on the left, cross over in the middle, exit on the right in 10 divisions. This is at 20 microseconds per division. Times 10 would be 200 microseconds. 200 microseconds would be one cycle. That'd be 5 kilohertz requiring that. Alright, we're at 0.1 microseconds per division. I want to go to 1000 hertz. I'm sorry, 10 kilohertz. Alright. We are now at 10 kilohertz. Just you see the red dot, and to the left is the 10. So we're at 10 kilohertz. 10 kilohertz. We are at 0.1 millisecond per division right now, and we are getting a cycle in every division. We can check that easily. enter half, exit on the whole. So there's one full cycle, one division. Times 10. Enter, crossover, exit, and 10 divisions. 10 kilohertz. There's 50 microseconds per division. I want to go to 20 kilohertz. Okay, I'm just touching up the focus just a little bit here. There we go. And let's turn the intensity down just a hair. I don't think we need that much. There we go. 50 microseconds per division. We are tracking, entering on the left-hand mark, crossing over in the middle, and exiting on the right-hand mark. We got one full cycle per division, and times 10 in the range, and we see that enter on the left, cross over in the middle, and exit on the right. Both cycles, both channels are cycling together in one cycle perfectly at 20 kilohertz. Okay. We go to 10 microseconds per division. I'm not sure, did I jump one? Must have jumped one. I want to go 20 microseconds per division. We'll go to 50 kilohertz. We get one full cycle per division. Perfect. Didn't even have to adjust it. And we'll go times 10. And there we are. Enter, crossover, exit, and 10 divisions, both channels, no problem. Alright, now we go to 10 microseconds per division, and I want to go up now to 100 kilohertz. Okay, we're at 100 kilohertz. We have one cycle and one division. Perfect. We can see it easier, times 10. Enter, crossover, exit. Maybe touch that up just a hair so it's easier. Enter, crossover, exit. 10 divisions. Perfect. Alright, and then we go to 5 microseconds per division. 5 microseconds per division. I want to be at 200 kilohertz. And I get one full cycle and one division, right on. Go times 10, and I get entry, crossover, and exit in 10 divisions. Perfect. 200 kilohertz on the sweep, and we are at 5 microseconds per division. Go to 2 microseconds per division. We're going to go up to 500 kilohertz. 1 trace per division is what we want. And that's what we got. 1 trace per division. And we have entry, crossover, and exit in 10 divisions at 0.2 microseconds. So I'll go back to the 2. Now I go up to 1 microsecond per division, and I want to step up to a megahertz now. Okay, there's a megahertz, 1 full cycle and 1 division, 1 full cycle and 10 divisions if I take my range switch up to 0.1 microseconds per division. Okay, we're ready for 0.5 microseconds per division. That would be 2 megahertz. And that is entry at the left side, crossover in the middle, exit on the right side. Again, 1 trace per division. Perfect. We are at 0.5 microseconds per division. and we are running 2 megahertz. Perfect. Okay. And we can take that up by 10, and we can see that we have entry, crossover, and exit, both traces together. Beautiful in 10 divisions at 50 nanoseconds per division. Pardon me, bug. All right, we go 0.2 microseconds per division. I want to go up to 5 megahertz. And we see that we enter on the left, crossover midway, exit on the right. Perfect. And I can still step up times 10 in the range and make my adjustment. Enter on the left, crossover in the middle, and we would exit on the right. The trace is disappearing on the right, but it's there. We can see where it would be. This is at 20 nanoseconds per division. Okay. Put myself back in the mid here. And then we want to go next step. This is 0.1 microseconds. 0.1 microseconds meaning that I'm going to want to go up to 10. And we should be displaying now in 1 cycle and 1 division. Not a problem. We are at the 0.1. You can see that there, 0.1 microseconds. And I can't give you times 10 range because that's beyond the capability of the scope. But I think we can see that we have 1 trace per division, so not a problem anyway. Let's go ahead and well, at this point, I need to switch generators. I need to switch to my PTS so that I can carry on. Okay, we've done a couple of things now. We've switched to the PTS generator for our last couple of steps. This is producing 20 megahertz. It also is a synthesized frequency generator. The 20 megahertz is being read on the 50 nanosecond per division scale, and we are getting 1 cycle per division, just like we should. Entering on the left, crossing over in the middle, and exiting on the right. And the last step is 20 nanoseconds per division, which require a 50 megahertz signal. And there we go. And once again, we are entering on the left, crossing over in the middle, and exiting on the right in every division. So we are accurate through every range of the horizontal. It's beautiful. Okay, now these last 2 ranges I measured independently on A, and I'm going to measure independently on B. And the reason was I was using this device for my crossover between the 2 scales, and I was getting too much loss in this cable at the higher frequencies, so I'm doing it independently for the last 2 ranges. We are now going to switch to B, channel 2, and put ourselves on tray. There we go. So now we are on channel 2, 0.2 volts per division, but doesn't matter particularly on the vertical. Channel 2 is selected. We are triggering on channel 2 as a source. We have one cycle and one division, just as we did on channel A. And we are right now at the maximum. This is our 20 nanosecond per division speed, and this is at 50 megahertz. If I go backwards to the 20 megahertz and step down to 50 nanoseconds per division, we also see that we have one cycle and one division, just as we did earlier. Okay, so channel A and channel B both beautiful. Okay, we're looking at a 40 megahertz signal here on the B&K coming from our PTS 160, and we're going to be stepping that 40 megahertz signal up to 100. Right now we're calibrated so that we have 4 divisions plus and minus over the amplitude of the signal. When that amplitude reaches 2.8 divisions, that would be the 3 decibel down point. So we want to see if that is at 100 megahertz. So here we go. Here's this is 50, 60, 70, 80, 90. There's 100. So let's go 101, 2, 3, 4. Looks like 104 megahertz to me. As best as I can get with this equipment, our amplitude has dropped to the 3 decibel point on channel B at 104 megahertz. Let's try it on channel A. Alright, here we are at 40 megahertz, channel A, plus or minus 4 divisions. And we're going to go to 50, 60, 70, 80, 90, 100. That's too much. Here's 101, 2, 3, 4, 5, 6. 106 megahertz. Possibly you could call it 7 even. It's a toss-up. 106, 107 megahertz, and we hit the 3 dB point. But that's it. And if I was to pull this knob here, we'll expand our horizontal divisions by 10. And you can see the waveform, 100 megahertz signal being displayed on the, it's actually 106 megahertz signal being displayed on channel A. So there you have it. Scope has checked out very well. Bandwidth checked out, our range is checked out, our vertical checked out. It's good scope, and it looks nice. There's a little bit of chemical spatter. I don't know if you can see it in the light or not. It's faint, but in the background of the faceplate there are some spots, like water spots, except they don't come off. They're faded. Really, you don't notice them, but I'm calling it to your attention just to let you know that Looks like some spray cleaner or something may have hit it in the past and made a little spot mark in the background. But outside of that, this thing is fantastic. So it will come with a full manual. This is a rather thick manual, and most of the pages are 11 by 17. I've included here so they're easier to read. It has all the layouts, the schematics, the signals. This goes through the calibration, the theory, everything. It's a service manual for a Kenwood CS1100A, but when you look at the scope on the front, you'll recognize that it's also the B&K, and everything about the interior speaks to that too. So Kenwood made this scope for B&K. Convinced of that. And I will include a set of 100 megahertz leads, so be in good shape. Okay, thanks for listening.